Aluminum doesn't exist in shiny sheets underground. In nature, it's trapped in an unremarkable rock. And to turn that rock into the silvery, lightweight metal we use everywhere takes one of the most fascinating industrial journeys on Earth. Before we dive in, if you love discovering how everyday things are made and the science behind them, make sure to hit that subscribe button and turn on the bell. That way, you'll never miss a journey like this one. From raw earth to the amazing materials that shape our world. Let's start at the very beginning. The source. The aluminum we use today starts its life in a rock called bauxite. Bauxite isn't rare, but the right kind of bauxite, rich in aluminum oxide, is concentrated in tropical and subtropical regions. Places like Australia, Guinea, Brazil, Indonesia, and Jamaica are the world's top producers. How does bauxite form? Over millions of years, rainwater and warm climates cause rocks to break down chemically, leaching away silica and other minerals, and leaving behind a high concentration of aluminum hydroxides. The result is a reddish-brown, soil-like rock that looks almost like clay, but hidden inside, it holds the key to producing aluminum. In the 1800s, aluminum was actually more expensive than gold. That's right. Napoleon III of France even reserved aluminum cutlery for special guests, while others got gold forks. It wasn't until scientists discovered efficient ways to extract aluminum from bauxite that it became accessible to the world. The journey from raw earth to shiny aluminum begins in the bauxite mines. These mines are often open-pit operations, sprawling across landscapes where the topsoil is carefully removed to reveal the reddish-brown ore beneath. This top layer, called the overburden, is set aside for later use in land rehabilitation, because when the mining is done, the goal is to return the land as close as possible to its natural state. Once exposed, the bauxite is scooped up by enormous excavators and front-end loaders. Each bucketful can weigh several tons, and the machines themselves are massive. Some haul trucks stand taller than a two-story building and can carry up to 150 tons of ore in a single trip. From the pit, the bauxite is transported along haul roads or conveyor systems to the next stage of processing. The mining sites are carefully planned in stages so that while one area is actively mined, another may be in the process of being restored. This rotation helps balance production needs with environmental responsibility. Mining companies also work closely with local communities and environmental agencies to minimize the impact of operations. In many countries, replanting native vegetation and protecting nearby water sources are legal requirements, not just best practices. What's striking is the sheer scale. From the air, active bauxite mines look like bold, red patches carved into the earth. On the ground, the work is a steady rhythm of digging, loading, and hauling, the first essential step in aluminum's long transformation from ore to everyday object. Every soda can, airplane fuselage, or smartphone frame begins here, in the careful and deliberate process of extracting bauxite from the Earth's crust. Without mining, the rest of aluminum's remarkable journey simply couldn't happen. Next, the bauxite is transported to crushing facilities. Huge steel jaws break the rocks into smaller pieces, and then grinders reduce them to a fine powder. Why? Because the finer the particles, the easier it is to extract the aluminum oxide in the next stage. Think of it like grinding coffee beans before brewing. The more surface area, the better the extraction. Now the real chemistry begins. The most common method for refining bauxite into aluminum oxide, is called the Bayer process, named after Austrian chemist Carl Bayer, who developed it in 1888. Here's how it works. The powdered bauxite is mixed with a hot solution of sodium hydroxide under high pressure. The sodium hydroxide dissolves the aluminum-containing compounds, creating a liquid solution. Impurities like iron oxides and silica don't dissolve. They're filtered out as a reddish sludge called red mud. The remaining liquid is cooled, causing the aluminum compounds to precipitate out as crystals of aluminum hydroxide. These crystals are then heated in giant rotary kilns to drive off the water, leaving behind a pure white powder, alumina. At this point, we're halfway there. Alumina may look like sugar, but it's still not metallic aluminum. For that, we need to break apart its strong chemical bonds, and that takes a lot of energy. Smelting is where the magic and the electricity happens. The process used today is the Hall-Héroult process, invented independently in 1886 by Charles Hall in the United States and Paul Héroult in France. In this method, alumina is dissolved in molten cryolite, a rare mineral that lowers the melting point, inside large electrolytic cells called pots. An enormous electric current, sometimes more than 150,000 amps, is passed through the solution. This breaks the bond between aluminum and oxygen. Pure molten aluminum sinks to the bottom of the cell, while oxygen reacts with the carbon anodes to form carbon dioxide. Every few hours, workers tap the pots, draining the molten aluminum into crucibles. From there, it's cast into large blocks called ingots, each weighing several tons. These ingots are the starting point for countless aluminum products. Once cooled, ingots are reheated and sent to rolling mills. Here, powerful rollers flatten them into sheets as thin as 0.2 millimeters for foil, or thicker plates for airplanes and ships. Alternatively, the aluminum can be extruded, pushed through a die to create long shapes like window frames, tubing, and car parts. The possibilities are endless because aluminum is incredibly malleable. It can be shaped, bent, and formed without breaking. Here's one of aluminum's greatest superpowers. It's 100% recyclable, and it can be recycled over and over without losing quality. Recycling aluminum saves up to 95% of the energy required to make it from bauxite. That's why recycling your soda cans isn't just good for the environment, it's an energy-saving powerhouse. In fact, a recycled can could be back on the shelf in as little as 60 days. Strong but light, corrosion-resistant, conductive, and endlessly recyclable. Aluminum's unique properties make it essential for everything from cars and planes to smartphones, skyscrapers, and even spacecraft. Without aluminum, modern life as we know it simply wouldn't be possible. If you enjoyed this journey into the world of aluminum, give this video a like, share it with a friend who loves learning, and don't forget to subscribe for more fascinating stories about the materials, science, and engineering that shape our lives. Until next time, keep exploring.
We take scrap material, we melt it down, then we send it through the rolling mill and we make rebar and we make T-post and then we ship it out.
Tell them, hey, mommy has a really good career.
Totally generated over and over again, and we just keep, we're a mini mill, we have some micro mills.
Bridges, buildings, any kind of roads. The new Texas Ranger Stadium all has our rebar.
Family, Steel Texas, that retired from there. My grandpa retired from there. I have an uncle in Steel Arizona. It's in the blood, you know, I like it, I love it.
CMC always recognizes hard work.
Every day, mountains of scrap metal are tossed aside. Forgotten relics of old cars, demolished buildings, and decommissioned machines. But what if we told you these discarded metals are being reborn as one of the most essential materials in modern construction? Welcome to the world of rebar, steel reinforcement bars that form the invisible skeleton of buildings, bridges, and highways. And in this video, we're taking you inside an eco-friendly steel factory to see how tons of scrap metal are transformed into high-strength rebar, ready to support the weight of the modern world. Stay tuned to discover the incredible journey from junkyard to construction site. Steel is the most recycled material on Earth. In fact, over 70% of rebar in the US is made from recycled scrap metal. And that's not just good economics, it's a sustainability win. At the heart of this transformation is a type of facility known as an electric arc furnace, EAF steel mill. Unlike traditional blast furnaces, EAFs don't rely on iron ore or coal. Instead, they use electricity to melt down existing steel, cutting carbon emissions by as much as 75%. In this video, we visit Greenform Metals, one located of the most advanced, eco-friendly steel plants in the world, just outside of Houston, Texas. The journey begins at the scrapyard. Each day, truckloads of ferrous scrap arrive at the factory. This includes shredded car bodies, demolition debris, steel beams, industrial cast-offs. A crane equipped with an electromagnetic claw lifts the material and sorts it, removing non-ferrous metals and contaminants. The selected steel is then sent to a pre-processing area, where it's shredded and sized to ensure consistent melt quality. Once sorted, the scrap is carefully weighed and conveyed to the furnace loading area. Now comes the heart of the process, the electric arc furnace. This massive vessel is lined with heat-resistant bricks and equipped with graphite electrodes that can generate temperatures over 3,000 Fahrenheit, 1,650 degrees. As the electrodes lower into the furnace, a powerful electric arc forms, creating a plasma field that melts the scrap metal in minutes. This process is not only fast, it's efficient. Thanks to renewable electricity sources like solar and wind, green-form metals achieves near zero carbon emissions during melting. Once melted, the liquid steel, called molten metal, is tapped into a giant ladle and transported to the next phase. But raw molten metal isn't ready to become rebar just yet. It needs refining. The ladle enters the ladle metallurgy furnace, LMF, where engineers fine-tune the chemistry of the steel. By adding small amounts of carbon, manganese, and vanadium, they adjust the strength and ductility. Impurities like sulfur and phosphorus are removed using fluxes. The process is closely monitored by metallurgists who take regular samples to ensure the steel meets strict ASTM standards for rebar. Once the composition is perfect, the steel is ready to solidify. Next up, continuous casting. Molten steel is poured into a mold that quickly cools it into a semi-solid shape, typically a square billet about 6 to 8 inches wide. The billet then travels through a series of rollers and water sprays to fully solidify while maintaining its shape. This continuous casting method is faster and more efficient than traditional ingot casting, with virtually no waste. The red-hot bills are then cut to length and sent to the reheat furnace for the final forming stage. This is where the transformation really takes shape. The bills re-enter a reheat furnace to bring them back to a pliable temperature. From there, they're fed through a series of rolling stands that progressively shape them into long, slender rods, each one with a ribbed surface to help concrete grip the steel. The ribs are not just aesthetic, they're engineered for maximum adhesion in concrete. Depending on the final use, the rebar is rolled into different diameters, typically ranging from 3/8 inch to number 18, 2.257 inch. The rods are then cut to standard lengths, usually 20 or 40 feet, and moved to the cooling bed. Before any rebar leaves the plant, it undergoes a series of rigorous tests. Each batch is sampled and checked for tensile strength, bendability, chemical composition, corrosion resistance. Only when it passes all quality control metrics is the rebar certified and stamped with a unique mill code, allowing for full traceability from melt to shipment. Once cooled and inspected, the rebar is bundled, tagged, and stored in massive outdoor yards. From here, it's loaded onto trucks or rail cars and sent across the country to skyscraper projects in New York, bridge repairs in California, and new housing developments in the Midwest. Each bundle represents not just a batch of steel, but a triumph of recycling, engineering, and environmental innovation. As the world races to decarbonize, industries like construction and steelmaking must evolve. And facilities like Greenform Metals are leading the way. By recycling scrap, using clean electricity, and deploying smart automation, they prove that heavy industry doesn't have to be heavy on the planet. In fact, every ton of recycled steel used saves 1,400 pounds of iron ore, 2,400 pounds of coal, 120 pounds of limestone, and reduces greenhouse gas emissions by nearly 60% compared to virgin steel production. Thanks for watching. If you enjoyed this deep dive into the world of steel recycling, don't forget to like, subscribe, and check out our next video, where we go inside a factory turning waste plastic into highway asphalt. It spins at over 1,200 revolutions per minute. It handles over 20 pounds of soaking wet fabric without breaking a sweat. It blends software, sensors, and sheer mechanical force to perform a task we depend on every single day. But behind this everyday convenience lies a world of laser precision, robotic engineering, and industrial strength. This is not just a washing machine. This is a triumph of modern manufacturing. Today, we go behind the scenes, inside one of the world's most advanced factories, to see how cold steel becomes a spinning marvel of technology. This is Top Discovery 4K. And this is how washing machines are made. The journey begins with steel, cold, coiled, and heavy. Each roll weighs up to 20 tons and contains hundreds of feet of high-grade galvanized steel. This isn't just any metal. It's engineered for strength, durability, and corrosion resistance, built to endure years of vibration, water, and friction. The coil is fed into a decoiler and leveling machine, which flattens out every curve and crease. Precision matters. Even a 1 millimeter deviation can cause the final product to fail under pressure. Next, high-powered laser cutters carve the steel into panels, destined to become the sides, base, and top covers of the washing machine. Each piece is programmed down to the micron. This isn't rough manufacturing, it's industrial origami. Then come the hydraulic bending stations. Here, robotic arms feed each sheet into precision presses, which bend and fold the steel with force equivalent to a car crash, yet with millimeter control. These complex angles aren't just for looks. They add structural strength, so the machine can handle the violent force of a high-speed spin without shaking apart. Each part comes together to form the chassis, the skeleton of the machine. And just like in nature, the skeleton must be both rigid and flexible, able to support heavy loads while absorbing constant vibration. Every weld is tested, every edge deburred. The result, a frame built to last over a decade of daily use. From raw coil to rigid frame, it all begins with steel. Strong, silent, precise. And this is just the beginning. Inside every washing machine lies its beating heart, the inner drum, a polished cylinder that spins, shakes, and swirls your laundry clean. It may look simple, but this drum is a product of high-precision engineering. First, a sheet of stainless steel is fed into a perforation press. Thousands of tiny holes are punched at lightning speed. They're not random. Each one is perfectly spaced to allow just the right balance of water flow and fabric protection. These holes let water in and out during the cycle, but they're also crucial for drainage, spinning force, and even energy efficiency. Once punched, the sheet is rolled into a perfect cylinder. Then a TIG welder, using a pinpoint arc of electricity, fuses the seam to create a flawless joint. No bumps, no gaps, because even the tiniest imperfection could shred your clothes or cause imbalance. End rings are added and crimped tightly. The central shaft, where the motor will connect, is mounted with ultra-precise bearings. Each drum is tested for balance, roundness, and weight distribution. At full speed, a wobble of just 1 millimeter can mean disaster. Next comes the outer tub, the watertight shell that houses the spinning drum. It's molded from durable polymer using high-pressure injection molding machines. These tubs are built to resist heat, detergent chemicals, and tens of thousands of rotations. The inner drum is lowered into the outer tub with extreme care. Rubber gaskets and vibration dampeners are installed, sealing the unit from leaks and minimizing movement. Shock absorbers and springs are attached, preparing the module to handle every drop, spin, and shake. It's strong, silent, and perfectly balanced. This is the part that does the real work, and it must work flawlessly, for years on end. To spin a steel drum filled with soaked towels at over 1,000 revolutions per minute, you need power. Silent, efficient,